Yes, solubility of a gas and a liquid depends on nature of the gas, nature of liquid solvent, T and P, temperature and pressure of the gas. Temperature and pressure of the gas. Now we'll take up two factors in detail. Number one, effect of temperature. Effect of temperature. Now for this, before I dictate, I'm explaining something. Be careful, listen carefully. See, when we dissolve any gas in a liquid, its physical state changes. It changes from gaseous to the liquid state. And when gas changes into the liquid state, it is nothing but liquefaction of the gas. And this process of converting gas into a liquid is an exothermic process. If you feel it's difficult for you to understand whether this is exothermic or endothermic, think of the reverse. Reverse means when you convert any liquid into gaseous state, like when you want to evaporate water, you have to supply energy. It is endothermic process. It means reverse of this is exothermic process. So when we dissolve any gas in a liquid, solution becomes saturated and there is an equilibrium established. Now, what is this equilibrium? Equilibrium will be gas in the gaseous state will be in equilibrium with gas which has gone into solution. They will be in equilibrium with each other and the process is exothermic. Now, if we increase temperature, now again think in terms of Lee-Chatelier's principle. When temperature is increased, equilibrium shifts in the backward direction, left-hand side. Shifting of equilibrium in the left-hand side means gas from the solution changes into escapes in the gaseous form. It means solubility of the gas decreases with increase in temperature. Right? Now start writing. A gas changes into liquid state after it has been dissolved in the liquid. After it has been dissolved in the liquid. Full stop. Thus, dissolution of a gas in a liquid is similar to condensation, which is an exothermic process. Exothermic process. In a saturated solution of gas in a liquid, following equilibrium is established. Note down this equilibrium. Gas and gaseous state, gas and solution plus heat. Pattern. According to Lee-Chatelier's principle on increasing the temperature, this equilibrium shifts towards left-hand side, that is left-hand side, that is solubility of the gas decreases with increase in temperature. So that was the effect of temperature. Now, second part, effect of pressure. effect of pressure. Now, today's remaining class will be on effect of temperature, because this will be a numerical based topic followed by many subtopics. Look at the board. I'm explaining something. Be careful. You don't have to draw anything, just try to understand. This is a cylinder fitted with a piston. There's a liquid in the cylinder. Above the liquid is a gas. Now, particles of the gas, molecules of the gas, they are in a constant state of motion. And when they move, naturally, some gaseous particles will strike the surface of the liquid. And due to moment of inertia, some gaseous particles which strike surface of the liquid, they go deep into the liquid, bulk of the liquid, and they remain there. That is, they will dissolve. It means we can say more the number of particles striking surface of the liquid, more will be the solubility. Now, if I increase pressure, this piston will come down. When piston comes down, number of gaseous particles per unit volume will increase. When number of particles of gas per unit volume increases, it means number of collisions of gaseous particles with the surface of liquid. Those collisions will increase, and therefore solubility of the gas will increase. It means we can say solubility of the gas increases with increase in pressure of the gas. And that's what you studied in 11th standard in the form of Henry's law. In 11th standard, it was only the statement of Henry's law that solubility of the gas increases with increase in temperature. But in 12th standard, this will be a numerical based topic. So write down the introductory part, effect of pressure. If a gas is held above a liquid, particles of the gas strike surface of the liquid. Due to moment of inertia, some molecules of gas enter bulk of the liquid and dissolve in it. When pressure of the gas is increased, number of gaseous particles per unit volume increases, their collisions with the liquid surface increase, and solubility increases. Next paragraph. According to Henry's law, Henry, according to Henry's law, amount of a gas dissolved in a particular amount of a liquid solvent at a particular temperature. Mentioning temperature is very important. At a particular temperature is directly proportional to pressure of the gas above the liquid solvent. Pressure of the gas above the liquid solvent. Now again, I'm explaining something. Look here. Again, cylinder fitted with a piston. There's a liquid at the bottom, and there's a mixture of gases. You can see I marked circles and crosses. It means I've shown particles of two different types. So if there is a mixture of gases held above the liquid solvent, naturally, particles of all gases of the mixture will strike surface of the liquid and then they will dissolve. Now, how much will be the solubility of a gas? Apart from nature of the gas will also depend on, I'll be a little slow now. How much will be the solubility of a gas of the gaseous mixture? Apart from nature will also depend on number of particles of the gas in the gaseous mixture. If particles of one gas are more than the second gas, it means first gas will have more solubility than the second gas, because more number of gaseous particles means more collisions with the surface of the liquid and more is the solubility. So I can say solubility of a gas is directly proportional to partial pressure of the gas in the gaseous mixture. Partial pressure means how much is the contribution of that gas to the total pressure of the gaseous mixture. So in simple words, more the partial pressure of the gas, more is the solubility, because more will be number of collisions. Now, I'll modify Henry's law. Statement will be modified. Be very careful. I said, if partial pressure of the gas is high, solubility of the gas in the liquid will be high. I can say, I'm modifying now. If partial pressure of the gas above the liquid is high, it means its mole fraction dissolved in the solvent will be high. Is that clear? Because high pressure, more amount of gas has dissolved. If more amount of gas has dissolved, it means I can say mole fraction of the gas which has gone into the solution, that mole fraction is high. Mole fraction will be high. This gives us the new definition of Henry's law, which we'll study in mathematical form. Right on, next paragraph. If a mixture of gases, if a mixture of gases is held above a liquid solvent, then particles of each gas present in the mixture will strike liquid surface and dissolve in it. Solubility of each gas of the gaseous mixture is directly proportional to its partial pressure in the mixture. Partial pressure in the mixture. Like if we consider air, partial pressure of nitrogen in air is more than the partial pressure of oxygen. So keeping that in mind, solubility of nitrogen should be more than the solubility of oxygen in any solvent like water. Continue, same paragraph. Thus, as the partial pressure, for partial pressure I don't PP, as the partial pressure of gas above the liquid solvent increases, its solubility increases. That is, its mole fraction in the solution increases. That is why Henry's law can also be stated as follows. Now here comes the second statement of Henry's law, which we'll be using in mathematical form. Right on. Statement: partial pressure of a gas above a liquid solvent is directly proportional to mole fraction of the gas dissolved in the solvent. Now you have to copy from the board. Mathematically.
Sir, I have a question.
Yes.
Sir, according to Henry's law, if the partial pressure is greater of one, say, gas, then how does this apply to our atmosphere? Like, if we have a greater partial pressure of N2 and our universal solvent is water, then how do we say that oxygen is more dissolved in water than nitrogen?
No, I never said oxygen dissolves more than nitrogen. Since partial pressure of nitrogen in air is roughly 4 times than the partial pressure of oxygen. It
Yeah.
means, according to Henry's law, solubility of nitrogen in water is more than the solubility of oxygen.
Yeah, so then how does marine life coexist?
See, that's what I'm in the beginning of this topic, and I think first or second sentence itself, I said it's a very small amount of oxygen which dissolves in water, but even that small amount of oxygen dissolved in water is sufficient for aquatic life. This small
Oh,
amount is not few grams, it is in millions of kilograms,
okay, okay.
right?
Hmm. Yeah.
Okay, mathematically, Pg directly proportional to chi g. We'll label it later on. Pg is directly proportional to chi g, or I can say Pg is equal to constant is kh into chi g. Chi g we can expand, it's mole fraction. You know the expression for mole fraction. Now we'll label all three parameters. Pg. Pg is partial pressure of the gas above the liquid. Above the liquid. Label this part chi g. Chi g is mole fraction of gas dissolved in the liquid. Now kh is called Henry's law constant. I'm giving 3 to 4 points about this Henry's law constant. Right on. Henry's law constant. Its units are the units of pressure. Its value is different for different gases. For the same gas, its value is different in different solvents. So if solvent changes, then for the same gas, value of kh will change. One more point, right on. It increases with increase in temperature. Now, last point I said, Value of KH increases with increase in temperature. Now look here. Product of KH and Chi, if KH increases, it means Chi will decrease. So we can say when temperature increases, KH increases. When KH increases, Chi decreases. Chi decreases means solubility of the gas in the liquid will decrease. I'll give a very simple example. If we take some tap water in a vessel at home and we put a living fish in it, it will survive because there is dissolved oxygen in water. Second case, we take the same tap water in a vessel, boil water. After boiling, when the water is hot, we cover it with the help of an airtight plate or cover, whatever. Allow this water to cool. After the water has cooled down to room temperature, now put a living fish in it. This fish now, it will die. The reason is at higher temperature during boiling, dissolved oxygen escaped because solubility decreases, and due to lack of oxygen, fish will die. So remember, solubility of gases decreases with increase in temperature. Next paragraph. According to this equation, higher the value of KH, lower is the value of Chi, lower is the value of Chi, that is, lesser is the solubility of the gas. Lesser is the solubility of the gas. That is why aquatic life is more comfortable in cold water than in warm water. In cold water than in warm water. I've shared one numerical, we'll solve it. You can check your WhatsApp message or you can see in the chat box. Numerical is calculate the mass of nitrogen that will dissolve in 4.5 liters of water at 25 degrees centigrade when the gas exerts a pressure of 0.98 bar. KH constant, Henry's law constant for nitrogen is so and so. Now, please keep on noting down and try to understand. Water, 4.5 liters means 4500 cc. Density of water is 1, therefore 4500 cc is nothing but 4500 grams. And this 4500 grams will be divided by molecular weight of water, it is 250 moles of water. Now I'll apply Henry's equation. PG, partial pressure of the gas is given 0.98 bar. KH, remember, partial pressure of the gas is given in bar unit, whereas KH is given in kilobars. Unit should be same. Therefore, 76.5 into 1000. This is the value of KH into mole fraction of nitrogen. Mole fraction of nitrogen will be number of moles of nitrogen divided by number of moles of nitrogen plus water. Water is 250 moles. Remember one thing, solubility of gases in liquids is generally very small, very low. That is why when you are calculating, neglect number of moles of the gas in the denominator. I'll repeat, when you are calculating numericals on Henry's law, neglect number of moles of the gas in the denominator so that calculation will become easy. Or otherwise you can try at home using calculator. It hardly makes any difference whether you neglect or not. So better is neglect. Next, calculate number of moles of nitrogen. This will come out to 0.0032. It means 0.0032 mole of nitrogen will dissolve in 4.5 liters of water. Convert into grams. So weight of nitrogen will be 0.0032 into molecular weight of nitrogen is 28. So this will come out to 0.0896. So you can see less than 1 gram dissolves in 4.5 liters of water. One more numerical I'm sharing. Yes. This numerical is major components of air are oxygen and nitrogen with approximate proportion of 20% and 79% by volume at 298 Kelvin. Water is in equilibrium with air at a pressure of 10 atm. It means pressure of air is 10 atmospheres. At 298 Kelvin, Henry's law constant for oxygen and nitrogen is so and so. Calculate mole fractions of these gases dissolved in water. See, first of all, check units of kH. Units of kH are millimeters. It means we'll have to convert pressure of the gas in millimeters. Right? Chaliye. PT means P total pressure of air. I hope you know 1 atm pressure is 760 millimeters. So 10 atmosphere will be 7600 millimeters. Now, partial pressure of oxygen. Oxygen is 20%. It means partial pressure of oxygen will be 20% of 7600. 20% of 7600, 1520 millimeters. Partial pressure of nitrogen, 79% of 7600. This will come out to 6004 millimeters. So these are the values of Pg for two gases. KH values are given and we'll calculate mole fractions. Now, Pg 1520 is equal to KH for oxygen. For oxygen, it is 3.3 into 10⁻⁷ multiplied by mole fraction of oxygen. This mole fraction of oxygen will be one answer. Let me tell you, the answer will be 4.61 into 10⁻⁵. This is one answer. Second, for nitrogen, partial pressure of nitrogen
Sir,
is 6,000. Yes.
sir, actually the board is not fully visible. Can you like tilt the screen a little? Yes,
Yes.
thank you, sir.
Okay.
Thank you, sir.
Now, partial pressure of nitrogen is 6004 millimeters and KH value is 6.51 into 10⁻⁷ into chi nitrogen. So this will give the second answer. It will be 9.22 into 10⁻⁵. These are mole fractions of nitrogen and oxygen dissolved in water. Generally numerical on Henry's law. comes once in, I think, every 2 years. Board में numerical is asked. Next topic, applications of Henry's law. Applications of Henry's law. There'll be 4 applications. I'll explain each and every application and then I'll dictate you. Look here. This is the bottle of cold drink, soft drink, Coca-Cola. There's liquid, and above the liquid, this bottle is never filled to the brim. Above the liquid, there's some empty space. This so-called empty space contains carbon dioxide gas at high pressure. You might have noticed when we open this bottle at room temperature, a fizzing sound, this sound comes. Now, when we open the bottle, this is CO2 gas at high pressure. If you think in terms of Henry's law, higher the pressure of CO2 above this liquid, more will be the solubility of carbon dioxide in the liquid. Now, when the bottle is opened, pressure of CO2 above the liquid will decrease. Now, again, according to Henry's law, when pressure of the gas decreases, solubility will decrease. And when solubility decreases, you might have noticed dissolved oxygen starts coming out in the form of bubbles, right? So that is the application of Henry's law. So number one, to increase the solubility of CO2, carbon dioxide, bottles of soft drinks are sealed under high pressure of CO2 gas. High pressure of CO2 gas. One thing more, you might have noticed that if you leave this soft drink open for a long time and then taste it, it gives a very bad taste. We call it it gives a flat taste. The flat taste is due to all oxygen dissolved that has escaped. In fact, when CO2 dissolves in water, it reacts with water to form carbonic acid, H2CO3. And this carbonic acid partly gives the taste. Second application, let me explain. See, when we breathe in, immediately air goes into our lungs. Then from lungs, how is oxygen transported to various parts of the body? Again, on the basis of Henry's law. So when we breathe in, partial pressure of oxygen in lungs is high. And due to high pressure of oxygen in lungs, solubility of oxygen in blood में क्या होता है? Hemoglobin. The solubility of oxygen in hemoglobin is high. So I can say oxygen in lungs dissolves in hemoglobin and forms oxyhemoglobin. We'll write oxyhemoglobin as HB. Now, from lungs, this oxyhemoglobin goes to various parts of the body, various tissues. In various remote parts of the body, concentration, pressure of oxygen is low. Again, according to Henry's law, due to low pressure of oxygen, solubility of oxygen in hemoglobin will decrease. And due to decrease in solubility, oxyhemoglobin will release oxygen. And this oxygen will be utilized for metabolic activities. Moreover, in tissues, partial pressure of carbon dioxide is high. After releasing oxygen, hemoglobin will pick up carbon dioxide because according to Henry's law, its solubility will be more and it will now be transported to lungs. That is second application. In lungs, partial pressure of oxygen in the inhaled air is high. Due to this, oxygen dissolves in hemoglobin to form oxyhemoglobin. Oxyhemoglobin, you can write oxy-HB. Full stop. In the tissues, partial pressure of oxygen is low. In the tissues, partial pressure of oxygen is low, so that oxyhemoglobin releases oxygen for utilization. Releases oxygen for utilization. Third application. See, as we go to higher and higher altitude, we go to hill station, atmospheric pressure decreases. When atmospheric pressure decreases, it means partial pressure of every gas present in air will decrease. And when we breathe in at high altitude, partial pressure of oxygen which goes into our lungs, that partial pressure is low. It means solubility of oxygen in hemoglobin decreases at high altitude. This is the reason various parts of the body, or you can say our body, gets low supply of oxygen. And this is the reason people which live at high altitude, they grow weak. We probably have the feeling that they live at high altitude. They have to go up, come down, go up and come down. So their life is hard. That's why they are weak. No, they are weak. Partly the reason is their body gets low supply of oxygen. Now, if we think of climbers who go to Mount Everest, go to high altitude, at very high altitude, partial pressure of oxygen will be still lower. And due to very low partial pressure of oxygen, supply of oxygen to brain decreases. And due to low supply of oxygen to brain, they are not able to think properly. And this is the disease which is called anoxia. Generally, they carry gases in the cylinder. But in case the gas in the cylinder is exhausted, then the situation comes due to low supply of oxygen to brain, they're not able to think properly, they're not able to decide what to do. And this is the disease called anoxia. Generally, a short note comes on anoxia. Right on. Number 3. At high altitude, partial pressure of oxygen in atmosphere is low, and therefore its solubility in hemoglobin is less. Due to low concentration of oxygen in hemoglobin, people living at high altitude, generally become weak. Next paragraph. At very high altitude, this we are talking about climbers. At very high altitude, partial pressure of oxygen further decreases so that brain does not get sufficient oxygen. That is why sometimes climbers are not able to think properly. This disease is called anoxia is called anoxia. Last application, number 4. This will be a bit lengthy application. Let me explain this. You know, deep sea divers, they are called scuba divers. They carry some gas in the cylinder on their back. Imagine if they carry air, normal jo air hoti hai, if they carry air in the cylinder. Air, you know, contains 80%, roughly 79, 80% nitrogen, and oxygen is very less, roughly 20-21%. So as the diver goes deep and deeper, pressure of surrounding water on his body will increase. Due to this, partial pressure of nitrogen as well as oxygen in the lungs will increase to a large extent. I'm talking about if diver carries air. So due to pressure of surrounding water on the body, partial pressure of nitrogen and oxygen in lungs will increase. Solubility of both the gases in body fluids will increase. Out of these two gases, oxygen will be utilized in metabolic activities, but nitrogen is not utilized. Although large quantity of nitrogen is exhaled out, but still some quantity of nitrogen remains dissolved and gradually it is accumulated in body fluids. It remains dissolved. So as the time passes, concentration of nitrogen dissolved in body fluids will keep on increasing. And this excess of nitrogen becomes poisonous. It is toxic. Now, when the diver comes towards the surface after finishing his work, pressure of water on his body will decrease. When the person is down, his body is compressed. When the person is coming upwards, his body is decompressed. So when the diver comes towards the surface, pressure on the body decreases, solubility of dissolved oxygen will decrease, and this dissolved oxygen will now be released in the form of bubbles. These bubbles, sometimes they block arteries, and this release of nitrogen is very painful, and sometimes it's fatal. This release of nitrogen leads to a sickness which is called decompression sickness. Why do we call it decompression sickness? Because the body is decompressed, due to which dissolved nitrogen is escaping. It is called decompression sickness, or this is also called, there's one more name given to this. I'll tell you. Yes, bends, BENDS, bends. This is the reason they do not carry air in the cylinder. They carry a special mixture of 3 gases with a special composition that I'll tell you. Right on. Number 4, for their oxygen supply, scuba divers, deep sea divers, depend on the compressed gas which they carry in cylinders. If the cylinder contains air, I said if, right? If the cylinder contains air, then partial pressures of N2 and O2.
So could you repeat that?
If they carry air in the cylinder.
No, so a little from like depend on the compressed gas.
Okay. Language may slightly change because spontaneously aata hai. For this oxygen supply, deep sea divers depend on the compressed air which they carry, compressed gas, not air for the timing, compressed gas which they carry in cylinder. So if the cylinder contains air, then partial pressures of N2 and O2, nitrogen and oxygen, underwater, underline these two words, underwater will be very high. Due to this, both the gases will dissolve in body fluids to a large extent. Out of these, oxygen is used in metabolic activities, but nitrogen is not. Due to this, concentration of nitrogen in the body increases, which is toxic, which is poisonous. Next paragraph. When the diver comes towards the surface, pressure on his body decreases so that dissolved nitrogen is released in the form of bubbles. These bubbles may block arteries and lead to a disease called decompression sickness or bends. Again, next paragraph. To prevent this, divers carry a mixture of, copy from the board, mixture of percentages, better you remember, 56.2% nitrogen, 32.1% oxygen, and 11.7% helium. Helium is used to maintain partial pressure of required oxygen. 11.7% helium, out of which helium is almost insoluble in body fluids. Almost insoluble. Solubility of noble gases is very, very low. Next topic. Limitations of Henry's law. Limitations of Henry's law. That on Henry's law is applicable under following conditions only. So there are three specific conditions when Henry's law is applicable. Number one, pressure of the gas should be low and temperature should be high so that the gas behaves as an ideal gas. So that the gas behaves as an ideal gas. Number two, second point. Molecular state of the gas. Molecular state of the gas in the solution should not change. Should not change. That is, the gas should not undergo ionization. Should not undergo ionization. That is why it is not applicable to HCl gas dissolved in water. Because when HCl is dissolved in water, it will ionize to give H plus and Cl minus ions. That is why it will not give exact results on calculation. There will be deviation, right? So Henry's law is precisely not applicable in such cases. Last point, number 3. Gas should not react with the solvent. Gas should not react with the solvent to form a new compound. So there should be no reaction between gas and the solvent. That is why it is not applicable to ammonia and CO2, ammonia and carbon dioxide dissolved in water. You know, ammonia reacts with water to form ammonium hydroxide. Carbon dioxide reacts with water to form carbonic acid. This is the reason for these two gases, Henry's law is not applicable. Either we can say it's not applicable, or we can say will not give precise result on calculation, that how much CO2 or how much ammonia has dissolved in water. Calculations will not be precise. So with that, we finish Henry's law. Now we take up a very small topic which will take 5 minutes, which we have at hand. Right on heading solid solutions. Solid solutions. First of all, this concept is, it doesn't mean ice cream is a solid solution. So don't think we dissolve a solid in a liquid and then freeze the solution. It becomes a solid solution. No. Solid solution means solution of a solid and solid. Now the problem is, when you mix solid with the solid, it will never be a homogeneous mixture. And if it is not a homogeneous mixture, it means it will not be a solution. Then how do we prepare a solid solution? We mix solids in appropriate composition, percentage, whatever you want. Then melt this mixture of solids. After melting, liquid will homogeneously mix. After melting, we cool it. It becomes a solid solution. Madam, solid solutions are those which are formed by mixing two or more solid components. There are of two types. Number 1, substitutional, substitutional solid solutions. Substitutional solid solutions. Look at the board. I'll explain in a few seconds so that when you're writing, it becomes easy for you. Let us say this is a crystal of one solid component. These are particles of the solid. From the crystal of this solid, if some particles leave and they are replaced by particles of the other solid. Substitution is replacement. So if some particles of solid from the crystal are replaced by particles of another solid, but the condition is particles which are going out and the particles which are coming in, they should have approximately same size. That is the main condition. Then this will lead to the formation of a substitutional solid solution. Madam, are those in which some particles of the crystal of one solid are replaced by similar particles, underline similar particles. Here similar particles means similar sizes, similar particles of the other solid component. For example, brass. Brass, is an alloy. It contains copper 60% and zinc 40%. Zinc and copper, they are adjacent elements in the periodic table with atomic number. This is 30 and this is 29, this is 30. So their atomic sizes are very close to each other. Atoms of one element can replace atoms of the other element. So this will lead to the formation of a substitutional solid solution. Second type, interstitial interstitial solid solutions. Interstitial solid solutions. Look here. All particles are considered to be spherical in shape. And if you put spheres together, there'll be small gaps left in between these spheres. What are these gaps called? These gaps are called voids. In fact, there was a chapter on solid state in 12th standard in the syllabus, but for the past 4 or 5 years, it has been deleted. These voids are given 8 different names. 8 terms are used for these voids. These voids are called voids, gaps, sites, depressions, interstices, interstitials. There are different terms used. If small atoms, small particles of one solid are present in these voids, then it will be called an interstitial solid solution. Simple. Madam, are those in which small particles of one solid component are present in the voids of the other solid component. For example, in steel and tungsten carbide. In steel and tungsten carbide, small atoms of carbon are present in the voids of iron and tungsten respectively. Iron and tungsten respectively. That is why tungsten carbide is extremely hard and used for making tools for cutting and grinding. Do you remember which other substances used for making tools for cutting and grinding?
Diamond.
So you can say this tungsten carbide is almost as hard as diamond. The reason is small atoms of carbon which are present in voids, these atoms will decrease malleability of the metal. And due to this metal or steel, whatever, this will become hard. Right, children? Please try to solve as many as questions you can. Time to time, if you make a system that you solve on an average 8 to 10 MCQs per day. In a week, 60 to 70 MCQs, because I'll keep on sharing these MCQs. In some questions, 4 options will be given. In some questions, no option will be given. You have to calculate, and the answer you have to match. And apart from that, those 13 assignments which I gave you, those assignments will be discussed in the class, right? And please make a separate register for assignments. Do not mix up everything in the same register, right? Charlie, you can log out now.
Thank you, sir. Bye.
Thank you, sir.
Thank you,
Bye,
sir.
sir.
Thank you,
Thank
sir.
you, sir.